Hey everybody, this is chapter 5 plus, meaning we're going to cover a lot of stuff here that's not in our book. We're still discussing linear equations, but we're also going to discuss their cousins, let's say. Some equations that are related to linear equations, but they're just a little different. You'll see what I mean when we get up to them. Anyway, we got a lot to cover, so let's begin. First of all, I just want to show you some like shorthand notation that we'll see occasionally in this presentation, and I might use it in the future. You might see it in some other book or website, so I want you to know what it means. Uh, we use the abbreviation LHS to represent the left-hand side and RHS to represent the right-hand side of any equation. So here we've got a left-hand side and a right-hand side. And in any equation, the left-hand side and the right-hand side have to be equal. So sometimes it can be a way to organize your work. If you've got like this monstrously large equation and you just want to write down, here's my work for the left-hand side, do it all down here. Here's my work for the right-hand side, do it all down there. You see it more and more as you get into more complicated and advanced mathematics. So I'm just introducing the idea here. If you don't like using that notation, that's fine. You don't need to, but I would like you to know what it means. And as for linear equations, those are going to be any equation in this form, where we've got a times x, where a is just some real number, and then we add to that a constant value, which is also a real number. And that constant might be 0. Just the a value could not be 0, because if it was, then we wouldn't have any variable in the equation, and that would be quite boring. The solutions to an equation are any values of the variable that make the equation true. And so here's our equation. Here's some work for the left-hand side. Here's some work for the right-hand side. We notice that they both give us 13, so that means that the value x equals 2 must be a solution to the equation. I just want to point out its values. Some equations are going to have more than one answer. This is how we're going to approach these. Step 1 is basically just analyzing the equation itself. So we're seeing how the unknown has been built up, they're saying here. So, like, is it being multiplied by a number? Or are we adding things to it? Are we cubing it? What's happening to the variable? Step 2, we're going to perform inverse operations. So these are things that cancel each other out. Some really popular ones are going to be addition and subtraction, and then multiplication and division. But there's also more, like if we have a square root, then we square it. Those will cancel each other out. If we have a cubed root and then we cube it, or just in general, if we have an nth root and then we raise it to the power of n, those will cancel each other out. And there are more operations out there with inverses, but I think that's a good place for us to start. Step 3, please, please, please check your solution by substituting your answer back into the original equation like we saw in this example here. If we knew that the answer was 2, or if we got that as our answer, this work in the blue boxes is checking it to make sure that it's right. And I'm making a big deal about this because what we're going to see later in this video, there are equations that have where our work will generate incorrect answers. Yes, doing the correct work will give us answers that are wrong, and we can only know that they are wrong by substituting them back and checking. I'm sorry, sometimes algebra is just like that. So always check your answer for every single problem, no matter how much you trust yourself. It's really important. Okay, here's 4 simple examples of linear equations. Hopefully you know what you're doing here. We're using inverse operations on both sides, and we see that each of them finishes with a check. If you'd like to spend some time with this, please pause the video now. I'm going to move on. This one is ever so slightly more complicated. We have 2 unknowns on the same side, but we're just going to follow the laws of algebra, combine like terms, and then eventually narrow it down to something easier. We can also have unknowns on both sides of the equation, so we're just going to expand the brackets, do the algebra, whatever, collect the like terms, move everything to one side of the equation, and then solve for x. You like that, how I said we're just going to do the algebra? Yeah. That's exactly right. Do the algebra. So here's an example. Again, pause if you want to read this one through, but I think we should all be comfortable with this coming in. And one more, whatever, we have fractions here, so we're going to get a common denominator, and then it's, again, hopefully straightforward. If this is not straightforward, please let me know. I hope I'm not assuming too much. I also assume that we could see the bottom of that. Much nicer. So now we're getting into the stuff that's not in the textbook, and we'll slow down a little bit here to cover these 4 little subtopics. First, I want to talk about just basic linear equations that have special solutions. Some equations are going to have no solutions. Some equations are going to have infinitely many solutions. Weird, so it's not always just one answer. Then we'll look at absolute value equations. So that's just changing one little thing about the linear equations. Then we'll see radical equations. So in the previous chapter, we saw radical numbers. So now we'll deal with variables inside of those. And then finally, I'll show you how to do some stuff with technology. So it's possible to have a linear equation that actually has no solution. And here's an example of one. As I simplify the right-hand side, we distribute the 6 in, and then we end up getting 3x plus 18. But on the left-hand side, we have 3x plus 20. You're going to want to draw your attention to the fact that it's 3x in both cases. So we could subtract 3x from both sides. They're going to cancel out, and that leaves us with 20 equals 18. And that's not true, right? That's just a false statement. When we get to such a point, that means really one of 3 things has happened. Either you have made a terrible mistake in your work, or I have made a terrible mistake and given you an impossible question by accident, or it was actually on purpose and the question was supposed to have no solution. So as long as you've written down your steps and you can follow back what you did, then hopefully you'll trust yourself and you'll say, you know, it's not my fault. Either the teacher screwed up or was supposed to have no solution, so let's just go with it. And you're going to write down literally just the words, no solution. If you're feeling really lazy, then I could let you get away with this symbol. It's like a 0 with a slash through it. And if you don't like that, you can also use the squiggly brackets and just put nothing in between them. That's kind of a more advanced way to write this down. It's called the empty set. Some of you may have seen that before. But for me, I just like no solution, or, ah, heck, if you just want to write NS, that's going to be fine for me too. Now here's an example of infinitely many solutions. When I distribute the 6 on the right-hand side this time, we're going to get the exact same expression as we had on the right. And we can stop right here. As soon as we see that it's the exact same thing on the left-hand side and the right-hand side, we know there's going to be infinitely many solutions. Because if I start canceling things out, I could subtract 3x from both sides. We get 18 equals 18, which is certainly a true statement. Or you could just subtract everything from both sides and get 0 equals 0, which is just as true. The point is, no matter what value we choose for x, the equation has to be true. Therefore, there are infinitely many solutions. And we have a few options for what we could write down in this case as well. Here's a bunch of options over on the right. Just pick whichever one of these feels right for you. If you like the word answer instead of the word solution, that's fine with me too, whatever. Here's what we're not going to write down. We will not say that x equals infinity, because infinity is not a number. So that is absolutely not even an option ever, ever, ever. And I should have said for the last one, what we're not going to write here is x equals 0, because that would be saying that 0 was a solution to this equation that we just said actually has no solution. So those are our special case equations for simple linear equations. All right, and in both of these, they're kind of easy to identify because there'll be no solution when we have the exact same coefficient of x, but then a different constant next to it. And there'll be infinitely many solutions, well, when they're both the same thing. And I guess that's going to be true for any equation. If we see the exact same thing on both sides, whether it's linear or something much fancier, there's definitely infinitely many solutions. But there will be more complicated looking equations later on that might also have no solutions, but we'll just have to wait until we get to those. Hopefully, some of you are already thinking ahead to linear graphs, and you can think about this geometrically, like what's happening here in these cases with infinitely many solutions and no solutions. We'll kind of touch on that at the end of this video, but we won't get into that until a later chapter. So next up on our list is going to be the absolute value of a number, which I'm sure most of you have seen the basics of before, but some of what we see here might be a little new to you. First of all, we got another vocabulary word here, modulus. It just means the same thing. It's absolute value. We have two different ways to think about what absolute value means. One option is the geometric definition, and that's to think about a number line. The absolute value just tells us how far away from zero a particular number is, because distances can't be negative. So 7 and -7 both have the same absolute value because the distance between them and 0 is the same. It's exactly 7 units. However, we also have an algebraic definition because often in mathematics it is very helpful to consider the same concept from multiple perspectives. An algebraic definition says that the absolute value of a particular number is equal to that exact same number if the number happened to be greater than or equal to 0. And it is equal to the opposite of that number if x is less than 0. Let's just throw two numbers in there just to make sure that makes sense. The absolute value of 3, well, that is equal to exactly 3, right? And that checks out because 3 is bigger than 0. Whereas the absolute value of -3, still equal to 3, but hey, isn't this the opposite of that? Yes, it is. And the number inside the absolute value in this case was less than 0. And yet a second algebraic definition is here, which is to note that the absolute value of a number is equal to the square root of that number squared. And that works for negatives as well, because we could take any negative number, say -3, we can square it to get 9, and then take the square root of that. And the square root of 9, as we discussed in the previous video, is just 3. There are a few properties of absolute value that I think it's worth knowing. First of all, the absolute value of any number is always going to be greater than or equal to 0. A lot of kids like to say that absolute value always makes the number positive, but that's not true because, of course, the absolute value of 0 is 0, and that's not a positive number. Second, this one's not going to come into play too often for us, but it is true. The square of an absolute value is the exact same thing as just squaring the number. So there's no difference if you happen to do both squaring and absolute value. I don't know. Maybe you think that's neat, maybe not. The next two I want to look at together are these two. This should look kind of familiar, kind of looks like some of the exponent rules we saw. Basically, if we have a product or a quotient within an absolute value, we can separate that into two separate numbers, each with their own absolute values. This one up here, I think that should be fairly obvious. The absolute value of a negative is equal to the absolute value of the positive, of course. And the last one, if we take any two numbers and take their difference, that absolute value is going to be the same as if we switch the numbers around. Of course, you can choose any two numbers you want to verify that that's true. Now, solving absolute value equations, this is what we're interested in. So it's important to note that if the absolute value of x is equal to some number a, then x, the number in the absolute value, has to be plus or minus a. Let's just see that with some numbers. If the absolute value of x were equal to 5, then I know x has to be either 5, but it could also be -5. Both of those numbers have an absolute value of 5. So we're going to use this technique when we solve absolute value equations. We're going to always split them up and solve two equations, one with a plus and one with a minus. So for this first one, we have 2x plus 3 in the absolute value. That's equal to 7. So we're going to solve two equations here. One where we have 2x plus 3 equals positive 7, and the other 2x plus 3 equals -7. Both of those equations should be easy to solve. We get two answers out. And Not shown here, but a very important step, as we just discussed, is to check both of those answers. In this case, they both work. If I put 2 in here, we're going to get the absolute value of 7, which is of course 7. And if we put negative 5 in there, we'll get the absolute value of negative 7, which is still 7. I think it's easier to use the plus or minus on this side of the equation, but you can, if you insist, use it on the other side instead. On the right, we've got another example, but this one's actually easier because I don't even need to split it up. We have the absolute value of some stuff, doesn't even matter what it is, but look at this, it's equal to a negative, and that's not possible. We can't have an absolute value equal to a negative, it has to be greater than or equal to 0, so there's going to be no solution in this case. We can also have an absolute value on both sides of the equal sign. We approach it in the exact same way that we just showed. We'll just choose either side of the equal sign to apply the plus and the minus to. Don't apply it to both, even though there's an absolute value in both. Just pick whichever side looks nicest to you and do it there. So these two equations will come out like this. So I split both of the problems up, and in each case I decided to take the right-hand side of the equation and use the plus or the minus there. And in the first, the green absolute value equation, I get two solutions, negative 5 and 3, and if you check both of those back in the original, they both work. However, on the right-hand side, I got one solution over here, x equals 1/2. You can plug that in, and it'll work out just fine. However, in the other side, I had negative 3 equals 2, so that's an indication that that part had no solution. So this is an absolute value equation that only has one solution. Here's one that's even worse. So I split the black equation into the two green ones. I solved each of them. We've got two nice solutions here, negative 3 and 1/3. But check them both. It turns out neither of these solutions works out in the original. This equation has no solution. What are we going to do with something like this? This equation has an absolute value inside of an absolute value. Take a deep breath. It's fine. We're just going to do exactly what we said we would do. We're going to work from the outside in here. So we're going to get rid of this absolute value first. We're going to do that by taking everything that's inside of it and setting it equal to either 2 or negative 2. After we do that, we can move the 3 over to the right-hand side in each of these, and then look, we just have two normal-looking absolute value equations. So we're just going to take each of them and split them up just like we did before. And I won't show the work for either of those, but you can verify that you'll get two solutions from each of them, and all four of those solutions end up working way back in the original. So this absolute value equation has 4 solutions. Wow, isn't that thrilling? I also wanted to take this opportunity to show another option for notation and how we write our answers. Some people will prefer to write out just the word or to suggest that there are 2 answers. But another way to do it is to use what is called a subscript. So that's my 1 and 2. They're kind of like exponents, but they're down at the bottom right. So we just say the first solution is 0, and then the second solution is negative 1. Last thing I want to say about these, sometimes we have to do a little more work to get the absolute value by itself, and that's really the first step. Before we can split any of these up, we got at the absolute value alone. So if I had something like this, I would basically treat it as though it were 3 plus 2x equals 7. So the first thing I'm going to do is subtract 3 from both sides, and then after that is done, I'm going to divide both sides by 2. And now I have an absolute value just like before, and you can do the work for this one yourself. You'll find out that the two solutions are 3 over 2 and 7 over 2. All right, and that brings us to radical equations. So we saw radicals in the previous video. Now we're going to solve equations with them. And the steps for these are, first we're going to isolate the radical, so get the radical by itself, just like we did with absolute values. And I wrote here in parentheses, or isolate one of the radicals, because there might be more than one, just like we had more than one absolute value in some of the previous examples. Second step is we're going to, big word here, exponentiate. We see the word exponent there. means we're just going to raise both sides of the equation to the appropriate power to get rid of the radical. So if it's a square root radical, then we're going to square both sides. If it's a eighth root, then we're going to raise both sides to the power of 8. Yikes, that'd be enormous. And then we're just going to keep doing this. So we might have radicals inside of radicals. We'll just keep breaking them down one by one. We'll solve it, and then we're going to check our answers at the end, just in case we find another tricksy question with either no solution or where some of the solutions don't work. So here's a few basic ones. These are all done in like 2 steps each or fewer. In each of these cases, we're just squaring both sides. The square roots cancel out, and we get a solution. All right, we can see that happening in all 4 of these. This one's a little bit more interesting. When we square both sides, on the left, the square root goes away. On the right, we get 9. We solve that, we get x equals 5. We check that solution, and we would put that back in here, and then we're going to get the square root of 9 equals negative 3. But that's not true. We discussed earlier that that would not be the case. When we take the square root of 9, it's equal to the positive 3. And by the way, we also knew it wasn't true right from the beginning because we have the square root of something equals a negative. And for the same reason, that's not going to be the case. It's the square root of something is just going to be positive. This is the principal square root. Here are 2 more. In the green one, we have to get the radical alone, so we subtract 5 from both sides, and then we square both sides, bringing us here, and then we just solve for x like normal. We get x equals 25. On the right, I think it's easier in this case to divide by 9 as a first step, bringing us here, and then squaring both sides. 20 squared is 400. That's not too challenging to work out. And then when we divide both sides by 16, we get x equals 25 again. However, we could have, in this case, actually squared both sides as a very first step. We would have to square the 9 to get 81, and then that would be times the square root of 16x squared, which is just going to be 16x. And then we have to square 180, so we get a giant number. But anyway, you work it all out, you still get 25 out of that. At any rate, I don't recommend doing it that way, but I guess you could if you wanted to. Here's 2 examples with a radical on both sides. But in each of these, again, we just square both sides, and we see that the radicals all go away. And then we have just a normal linear equation to solve. And again, we always want to check our answer to make sure it works in the original equation, and in all these cases, they do. Here's another one with a radical on both sides, but when we square both sides here, we end up with a false statement. 4 equals negative 7. That's no solution. The difference in this case was, we could see it right from the beginning, we have 1x and 1x inside of our radicals, whereas in these examples, it was 2x and negative 2x, so those are different coefficients, and then negative 1x and then 1/2 x. So when the coefficients were different, let me say it could work. I'm not going to guarantee that it will always work. But here where we had the coefficients being the same, it was going to end up giving us no solution. Or I guess it could give us infinitely many solutions had the constant value been the same. Of course, I've got to talk about higher powers. So if we have a cubed root of 2x, guess what? We're going to raise both sides to the power of 3. And then 3 cubed is just 27. Divide by 2, we're done. And over here on the right, that's the 5th root. So we're going to raise both sides to the power of 5. The radical goes away, and our right-hand side is just 32, and then we can solve from there. We could also have radicals inside of radicals. So on the left, if we raise both sides of this equation to the power of 3 to get rid of the outer radical, that'll leave us with a square root of x equaling 8, and then we square both sides and find that x is equal to 64. On the right, we square both sides to get rid of the outside radical, and then we subtract the 4, and then we square both sides and find that x is equal to 25. And, let's have fun with it. I mean, we can have a lot of radicals in a single problem. So here, we're going to square both sides to get rid of the outside radical. And then we can subtract 1 from both sides, making that equal to 0. And then we're going to square both sides again to get rid of the next radical. We'll subtract the 1 over one more time. And then we're going to square both sides again. No, we're not, because here we have a radical equaling a negative. That's not allowed. There's no solution to this equation. Womp, womp. Now, I know that wasn't totally satisfying, so here's another one that can be solved. I've given you the answer already. You can just verify that you understand how the process goes by filling in the steps to get there. But anyway, I want to move on now to the final thing I wanted to share, which is how to do a whole bunch of this stuff on technology. And I'm going to show you some things that are allowed in my class. I'm going to show you some things that are not allowed in my class, but they still might be allowed on like an SAT or an AP exam or something like that down the line. So the first thing I'll show you is on the main calculator screen. So from the home page, again, never using the scratch pad. We're going to go down here. We're adding a calculator screen. So we're going to press menu. Everything good happens in the menu. And I guess what we're doing today primarily is algebra based. So I want to go in there, and we're solving equations, right? So the one that sticks out to me right now is number 1, solve. And by the way, I'm demonstrating this on a CAS calculator. We can see that right there. If you're using a non-CAS calculator, then you're only going to have a few items in here. And that's okay. I'll address you separately in just a moment. So we're going to choose solve. And you know what? Let's actually solve the equation that we just saw before. Basically, I'm just going to type it in exactly as it appeared on screen. The square root button on this calculator is right here next to the 4, and it's above the x squared. If I want to access anything that's they're in blue on my calculator, any of the things that are above the buttons, I just press the blue button first, the control button. So control x squared, that gives me a square root. And I can start filling this in. So it's 1 plus square root, keep going. And then right now my cursor is still underneath the final most inside radical, so I need to click to the right a few times until I can get it out of there. And then we're setting that equal, so the equal sign's right here, to 2. Now if I just enter this, it's not going to work. The calculator doesn't actually know what we want it to solve for, so we need to tell it. So if we want the calculator to know that x is the variable that we're interested in, at the very end of the equation, we just go down here to the bottom left-hand corner, and there's a comma button, and then we type x. And that's telling the calculator, I want to know what x is. Press enter, and it gives us the solution. Isn't that amazing? If you do not have a CAS calculator, then from the menu screen, you would just choose numerical solve. This will appear on your screen as well. And then the exact same thing. We type it all in, comma x, press enter, and it gives us the answer. Here's the difference between nsolve and solve. When we have an equation that has more than one solution, nsolve, it only gives you one of the answers, whereas solve would give you all of them. But here's the thing. You're not going to use this technique in my class. If you just use that on a test and then write down the answer, I'm not going to give you anything for it. I want you to know that this exists because this will help you check your work really fast, and in a later math class or exam setting, it might be helpful for you to use this technique, but I'm not going to give you any credit for it. What I will give you credit for, however, is using a graphical method. So this is exciting. We're going to learn some stuff now. So we're going to go back to the home screen, and we're going to choose a graph, which is the second option. So we're going to take the entire left-hand side of the equation, and we're going to put it here in this blank where it says f1 parentheses x, or that's read out loud, f1 of x. Some of you may have seen f of x notation in the past. If you haven't, don't worry, we'll learn that later this year. Then we want to enter in the right-hand side in a new line here. Now, if I press enter, it's going to graph that thing, which looks kind of like a straight line, although it's actually not. It's actually curving ever so slightly. But now I can't type in the other equation. So the way to get that line back is to press tab. And there we have the second line. Now I could have also not pressed enter, and instead from this screen we could just press down and it would bring me to f2 of x. If I press down again, it'll be f3 of x and f4 and so on. Anyway, back in f2 of x, I'll just type in the right-hand side of the equation, which was 2. Now that is a horizontal line, and that is exactly at the y value of 2. And now I'm going to search for these two graphs intersect with each other. It's clearly happening somewhere out here to the right, although it's not obvious to see where, so we just have to go looking for it. One option is you can press Control and then the center button here, and that'll actually enable you to grab the screen, and then you can drag it over. But we already know the answer is in the 3000, so that's going to take a long time. Instead, what I would say is go to the menu, and then we're going to change the window/zoom. I recommend usually that you not just press zoom out a whole bunch of times, because it's possible that you could zoom out so far that you can't actually see what's happening. So I like to actually play with the window settings. This gives you a little more control over what's happening. So I'm just going to choose 4000 since I know that's big enough. And we can see that they're getting closer and closer together, and maybe they intersect somewhere over there. Where we're going to find out for sure is we're going to go back to menu. We're going to analyze the graph and then find the intersection. When we click that, down in the bottom left-hand corner, it asks us for the lower bound. What this means is the calculator wants us to move this vertical line to be somewhere to the left of the answer. And we don't know where the answer is, but it's definitely not over here. So I'll just choose that. And as soon as I click enter, you'll notice that the words down in the bottom left-hand corner change. Now it says upper bound. And if I drag to the right, the calculator is now going to search in between those two lines for the solution. And if I just keep dragging, eventually, not really sure. Well, it's coming in and out. Oh, there we go. There it is. Nice. Now, my calculator actually gave it to me in scientific notation, which was unintended, but I'll leave it there just as a reminder of what that means. This is 3.97 times 10 to the third. If your calculator is saying that and you don't want it to, because I don't want it to, the way we're going to fix that is to go to Menu, Settings, and then we're going to change this from float 3 to just float. Float tells us how many digits are shown in a number. So I'll just press OK, and you see already it's fixed itself automatically. So 3,969, that's the x value where these two graphs intersect. The y value, 2, is actually not important to this problem. So now I want to show you absolute value. And what we'll notice is that for most of these, we're going to get some sort of a V-shaped thing. And we can talk more about why that is later on after we've discussed the graphs of lines. All right, so the left-hand side of my equation in this case was the absolute value of x minus 7. And the right-hand side was another absolute value. So here's how we can get that. Actually, first let me show you how we can't get it. A lot of people think that if they press Control equals, bring up this screen, that this symbol should be an absolute value bar, and it's not. I promise it won't work. So here's two ways we can do it. The first way is we can press this button here. I don't really know what to call that button, but it's right next to the 9. If we choose that, then there's a whole lot of prompts here. Oh, this is actually another way that we could get a square root, by the way, to show up. Didn't think of that before. But right there, that's an absolute value. So we can just press enter, and then we can type in what we want inside of it. And the other way we can do it is we're going to start typing down here A, B, and I'm going to type S, but before I do, notice right now that the A, B, they're in italics. So the calculator is currently interpreting A, B to be some variable. But as soon as I type the letter S, notice that they change and they're no longer in italics. That means that the calculator knows that the combination of letters A, B, S means something special. It means the absolute value. So I just type parentheses, and then whatever I want to go inside my absolute value, I put in there. All right, so when I graph this, I'm going to get this second V-shaped thing, and I want to find the solutions to it. One of them appears to be right here, but if you look carefully, it looks like these two lines are going to intersect somewhere up here. So let's find the two solutions. I could find the first one right away, but you know what? I'm just going to change the window so I can see the second solution first. I'm not exactly sure how high up I need to look, but I want to change my maximum Y value so that I can see farther up, and hopefully I'll find it. So I'll choose 50 and see how that goes. That was more than enough. I now see two intersections, and I'm just going to figure out what they are by choosing Analyze Graph. Intersection, lower bound. I'm going to go to the left of the first one. I'll press Enter, I'll scroll to the right, and as I do, it gives me the first intersection. So -5 is one answer. And then I'll press Menu, Analyze Graph, Intersection again. And now in this case, I don't know why that keeps happening, sorry. I don't want to move my boundary to the left of the first one. I only want it to be to the left of the second one. So I'll press Enter and I'll scroll to the right, and now I have my second solution. This was an example from earlier that had no solution. The equation was the absolute value of 2x minus 1 equals x minus 2. Doesn't look like these two are going to intersect. They seem to be getting farther apart up here, so we say there's no solution. This also works on desmos.com. Again, we can just type ABS, but you can also get the vertical bar that's on your keyboard kind of right above the Enter symbol, or the Enter button. If you just press that, it'll open up some absolute value that you can fill in. So this is an absolute value inside of another absolute value. So this actually gives us a weird kind of W shape. And this one's going to have 4 solutions. On Desmos, it's a little bit faster to find them. You just kind of mouse over and click. And again, it's the X values that we care about here, not the Y values. Now this is great. How are you going to use this on an exam? Like, how will I know that you use this method instead of the other method that I told you you're not going to be able to do? Well, it's easy. You're just going to draw the picture. And if you can draw the picture neatly enough, then I'll know that you did it right. And things don't need to be perfect. Here's our original on the left. Here's my version on the right. I'm going to draw my X and Y axis. You know what? It would be really great if we could all just agree to label those, yeah? And then I'm going to draw the first picture. It's a W thing. It looks kind of like this. I made sure that this point was to the left of the y-axis. I made sure that these 2 points are on the x-axis. That's really as neat as I need to be. I might label them like this is -2, this looks like it's 1. Not super important though. Now I've got the second line, which is going through it a couple of times. And I'm just going to label those 4 points. That's -2.4. That's -1.33. That's 3 significant figures. I'm good with that. This one's 0. And this one's 2.67. If you want to be really super awesome, then you can draw right in the y values as well. But again, it's the x values are the answers to the equation. So that's really what we're interested in. So if you can show me that picture, then I'll trust that you use your technology in an appropriate way, and I'm good with that. And this will work for absolute value equations. This will work for radical equations. It'll even work for simple linear equations, although I really hope that for the easy stuff, you can do it faster by hand. And as I said previously, this isn't cheating. Technology is an important tool. There's going to be things later on that we can only do on the calculator, so I want you to start getting comfortable with it now. So please, even if you prefer to do things by hand, that's amazing. Just practice it once or twice with the calculator so you know how to use the basic functions. Finally, oh my gosh, we got to talk about Section C. Lucky for you, I don't have anything to say except for this screen. Section C is just talking about word problems and translating them into equations. So we read the problem, we figure out what the unknown is that we're searching for, and we're going to give it a variable. Then we're going to write out an equation that states what we have in all the words. We're going to solve that equation through the appropriate methods. We're going to check our solution. And it would really be wonderful if we could actually write our answer out in sentence form, like within the context of the original question. A lot of people are just focused in math class on like, hey, what is the numerical answer? But I think it's important that we remember that mathematics has, sometimes at least, has a context in the real world, and we should keep that in mind when we're reporting our answer. Now, I'm not going to do any examples out of section C, partially because this video has gone on forever, and partially because every single question is going to be different. And so it doesn't matter if I show you one example or two examples or 20 examples, there are still going to be plenty of other questions out there that look totally different. And you need to get comfortable with the just the overall idea of translating word problems into equations and then solving them rather than trying to like copy a specific problem's steps. As I've said many times, this course is about problem solving and figuring things out in new contexts. It's not about just copying what you did on one question to another basically identical looking question. Anyway, I know what you're all thinking right now. When is this guy going to shut up? Well, I've got an answer for you.